million rods, 7 million cones that have the capability of resolving, when you put your brain behind them, 2 headlights on a car 39 miles away. So lots of future demand if, in fact, we want to deliver video to people in ways that that people can really appreciate. And all those things are going to create future demand, and I haven't even started to talk about all of the applications. So, how do you create more spectrum? Well, you only have a couple of technological choices. You can extend the useful range of radio. We started out with Marconi and the spark gap transmitter with a total bandwidth of 1 megahertz or less. Today we are up to around 3 gigahertz, and we're not going to go much further. And the reason is very simple. There are actually two reasons. One is people talk about the range of high frequencies is shorter. That's really not true. It's the antenna. You've all noticed that as you go up in frequency, the antenna keeps going, getting shorter and shorter. The antenna is a transducer. It literally is a hole through which all this energy has to go out into the open. And when you start getting up into frequencies above 3 gigahertz, it's much, much harder to get energy out into space. More importantly, above 3 gigahertz or so, all of a sudden the leaves on the trees, the rain, and all kinds of man-made obstacles start giving you a hard time. So we've pretty much gotten there. We're not going to get much improvement in the size of the spectrum from extending the range of frequencies. We can use more efficient technologies, and we have in fact done that. We started out with the spark gap transmitter. We went to AM, FM, digital FM. We are still improving, but back in the 1940s, Claude Shannon came up with a theorem that said that for a given signal of noise, there is an absolute limit to the amount of data that you can pass through a channel. And we're very close to Shannon's limit. We're not going to get much more improvement. You go from CDMA to wideband CDMA, there are advantages, there are higher speeds that will accrue, but we're not going to get much more spectral efficiency. We can do time sharing, and we have in fact done that. If you're familiar with trunk systems, where we had people of like usage sharing a channel and occupying that channel only while they were talking. When they stopped talking, somebody else could talk. And that has worked extraordinarily well in land mobile. Very hard to do when you have users that have very different characteristics. And you do start running now with time sharing into regulatory barriers, because when people own spectrum, they just hate it when other people intrude on their territory. And the final method is that we constrain communications to the minimum area that those communications occupy. Back to this issue of exclusivity. Let's keep that exclusivity down to only the people only the area that is really occupied by the people. It turns out that if you examine that curve that I showed you before about spectral efficiency over the years, it turns out almost all of the improvement has been in that form of efficiency improvement. Geographic sharing. If you can cut the amount of space that somebody is using when they occupy a piece of spectrum, that the remaining space is now available for other people, and that, it turns out, where it was the major portion of the historical improvement in spectral efficiency, it's going to be almost all of the improvement in the future. So how are we going to do this? How are we going to solve this conundrum of a perceived but non-existent existing spectrum scarcity? Most of this improvement is going to happen because of a technology that we have coined a term for, multi-antenna signal processing. Boy, that's a mouthful. Call it MAS. It involves just what it says, putting multiple antennas at one or both ends of a communication system and processing the signals from those antennas in such a way as to optimize communications between the two transmitter receivers. MAST includes a whole bunch of technologies, and I'm sure you've heard of all of these terms. Smart antennas, adaptive arrays, MIMO, spatial multiplexing, space-time coding. It's one of the things that we engineers do is come up with arcane ways of expressing really very simple technology. But the fact is that MAST today is deployed over some 300,000 base stations serving some 20 or 30 million people in China, Japan, and a whole bunch of other countries. This is not technology that is unproven. Furthermore, most Wi-Fi access points use a form of MAST today that improve both their range and coverage. Most importantly is that in WiMAX, mobile WiMAX, which is just starting to be deployed at first, there's only one system in operation today that's in Korea, but later this year there will be a number of trials starting all over the world. Inherent in the standard for mobile WiMAX is the use of MAST, of smart antennas, of MIMO, at both ends of the system. Multiple antennas in the user device, multiple antennas in the base station as well. For those of you that are not real familiar, let me give you an analogy, or maybe a couple. Let's assume that we've got a base station with just two antennas. We have a handset at some distance that is transmitting. Each of these antennas now gets a copy, receives a copy of the signal at a different point in space. We take these two signals, convert them to a digital form so we can do some processing. We now have the ability to do a couple of interesting things. One thing we can do is combine these signals constructively, add them together. The result of that, and by the way, there's noise on this channel as well. Remember about Shannon's theorem? When we combine the two copies of our signal, we'll get a signal twice as big. When we combine the noise, we get a signal that is only slightly bigger. So we now have improved our signal-to-noise ratio. But we can do another interesting thing with these two antennas. We can subtract these signals. We can literally take the two copies of the signal that we've gotten from this mobile, subtract them so that nothing is there. And we can do those with the wonders of digital processing at the same time. So if we have two users, we have one here, and we want to enhance him. He's the guy we want to listen to. We add his together. We've got another person here that's interfering. We can subtract those signals and literally cancel that person out. Very simple form, but very accurately described form of what smart antennas can do. I discovered some time ago, I used that analogy with some people just can't think about adding and subtracting signals, so I have another way of describing this. This is going to be somewhat inaccurate, but if I walk around this room and I didn't have this microphone on, you could you could close your eyes, and at any point in time you could point right at me. Now, how do you do that? You do that in exactly the way I described. You get two copies of the signal, of the sound of my voice. These two copies are out of phase. Your brain does a lot of processing, and it literally calculates where I am at a given time. Try that if you haven't done it. It is amazing how precise that is. And it's that same principle, except that we can do some much more interesting things with electronics. We're not constrained to just two ears. We can have lots of ears, maybe a dozen. We're not constrained to one mouth coming out. We can actually be transmitting with multi-antennas as well. And the benefits of smart antennas multiply when you do that. By the way, one way that you unconsciously have benefited from smart antennas using your ears, if you've been to a cocktail party, you notice two things. You could be talking to somebody and there's a din around you, and somehow you can extract their voice from the din because you're using the smart antennas and you're focused on them. But another interesting thing is that Tom is standing at a party talking to somebody, and the guy behind him says, Hazlitt said, and he can change his focus and listen to the guy behind him and totally ignore the guy he's talking to without moving. That's called adaptive array technology. And you use that all the time.
So it's not bad manners.
Only if you let the guy know you have done that. So here's what you get from multiple antennas. You get increased range because you can do this thing about adding signals together, better coverage. You can lower your interference because now you can cancel out any users, and for those of you that are technically oriented, if you have n antennas, you can cancel out n-1 users, sometimes even n. You get higher capacity because now, since you have rejected a whole bunch of people, you're only listening to the people that you want to listen to. You get huge increases in capacity and data, not all at the same time, but you have your choice between that. And the net result of all this is lower dropped calls, better spectral efficiency. But listen, you can do most of those things just by spending a lot more money. You could take a cellular system, for example, and just add a bunch of cell sites. The advantage of MAS, of mass, is you can do this with much, much lower cost. And that is the huge benefit that's going to happen. That is the revolutionary thing that's going to happen with the advent of this technology. So, when I simply said, I could have said this at the beginning and saved a lot of time. No, we don't have to change the way we allocate spectrum. If we make enough spectrum available through creative technology, I believe that broadband wireless delivered at affordable cost, and cost is the crucial issue. When the cost goes down, the applications will come, and they're going to be a lot more important than delivering music, MTV, playing games. Our whole medical system is going to be revolutionized when there is, in fact, true low-cost, reliable broadband service available. Spatial technology that I've been talking about, mass, is here today. It's going to deliver those kinds of solutions. But we are going to have to get better at using the spectrum. The fact is that reshuffling the frequency assignments, which we spend a lot of time doing, really doesn't give us much improvement. All we're doing is moving hunks of spectrum from one place to another. Reneging on old deals, boy, is that hard to do. Look how many years they tried to do, and they still haven't succeeded in getting the broadcasters to give up a lot of those guard bands. Applying immature technologies won't work. There are no magic solutions. It really does take 20 years and longer to get a new technology understood and embedded. The fact is that changing the regulatory process is often politically impractical. The way to solve the problem is to create new spectrum, mass, multi-antenna signal processing. It's already embedded in next-generation wireless systems, like WiMAX, like wideband CDMA. It's been demonstrated to improve spectrum in many places in the world. There are massive engineering resources being applied today. Every major corporation and a lot of small companies are now engaged in creating smart antenna technology, and mass is going to create new spectrum faster than we consume it. We've never run out of spectrum. We never will. Thank you very much. The floor is open. I don't pretend to be an expert in regulation, but there are a couple of things that we could do. And I'm not suggesting these are necessary. If we have enough spectrum, they really aren't. I know that the FCC has tried very hard to figure out different ways to get people to pay for the spectrum.